Now that we have a clear understanding of the intuition behind the KNN classification model, not only that, we have also looked at how exactly to operationalize this intuition of distance or similarity. Now that we've looked at all that, let's go ahead and take a look at actually how to build KNN classification models. Okay, so once again, here we have our data. As we've already said, the data set has to be, the predictors have to be normalized. And here is a data set in which we are showing only the two normalized predictor attributes. We're considering only two attributes, but the same thing can be extended to as many predictor attributes as we want. The distance formula is still the same. It's just that instead of having two terms in the square root, it'll have many terms. That's it. So other than that, everything else is the same. So I'm showing you an example here with two predictor attributes, both of which have been normalized. So we've got two normalized predictor attributes and you've got a target attribute. Now, when doing KNN, we have to divide the data into three partitions. Okay, now for trees, we built only two partitions. We did a training partition and a test partition. Now, when it comes to KNN, we actually have to create three partitions. Okay, so I'm calling the first partition as training A partition, and I'm also calling it the model. Shortly we'll see why I'm calling that as the model partition. Okay, in fact, model partition might be a better name for it. Okay, so we create a training A partition, and then we create another partition which I'm just calling as training B, and of course, as usual, we have a test partition. So there are three partitions. And roughly what I've done is divided the data into 50, 25, 25. Okay, a half going into training A and a quarter going into training B and test. Okay, now if you really look back, the real training partition is this one. What I'm calling as training.B is the real training partition, and this is the test partition. Okay, so in order to train the model, essentially what we'll do is we will generate predictions for all the cases in this partition. Okay, in the training B partition, we will generate predictions. We will look at how it performs on the training on this partition, and then we'll go ahead and evaluate it on the test partition. Okay, so we'll be using the training A partition only to compute the nearest neighbors. Okay, so this is our training partition, this is the test partition. The training A partition is used only for finding the k nearest neighbors. Okay, so understand that. So don't get confused thinking that this is really a training partition. It's actually not a training partition. This is a training partition, this is a test partition. Okay, so let's take a look at a concrete example. So here we've got the training partition, training A partition, and this is a training B partition. Think of this as the real training partition. Okay, so since this is a training partition, what I want to do is to make predictions for every case of this partition. Okay, so now let's say we want to make a prediction for this first row. Notice again that in this partition also you're only looking at normalized values, normalized values. So before we create the partitions, we would have normalized the data, and that's what I showed you. Okay, now in order to classify this first case, let's assume k equals 3. And later on, I'll show you how we find the correct value of k. Okay, so we've got k equals 3, and we want to find the k nearest neighbors for this partition. Okay, so let's say that you've done the computations, I have done the computations, and it turns out that the nearest neighbor is this guy, the second nearest neighbor is this row, and the third nearest neighbor is that row. Okay, so which means what? Which means that we took this case and we computed the distance to all of these cases, and after that we found that this is the closest, this is the second closest, that's the third closest, simply by virtue of distance, and we know exactly how to calculate the distance. Okay, so how do you classify this case? Well, it turns out that all its three neighbors are non-owners. Okay, which means the majority is non-owners, and therefore we are going to classify this as a non-owner. Okay, and in fact it turns out to be a non-owner as well. So that's a correct classification. And if you want to compute the probability, all we're going to say is, well, probability of it being a non-owner is 1, and the probability of it being an owner is 0. Okay, so this is what we're going to do. So this is how you calculate. Given K, given a value for K, and given the training B partition, we know exactly how to classify every case of the training B partition, right? So we'll repeat this step for all the rows. And therefore, we will have the prediction for every single row for this value of K. Okay, so in K nearest neighbors method, what we actually do is we repeat this process for many values of K. So this is what is going to happen. So you've got the normalized income, normalized lot size on training.b, you've got the actual ownership, and then we generate the predictions with K equals 1, K equals 3, K equals 5, 7, 9, up to whatever level you want. Okay, typically we don't consider more than about 10 neighbors. Okay, so typically 1, 3, 5, 7, 9 in case the target attribute has 2 classes. Okay, so you do this, and then based on that we can now calculate the error matrix for every level, right? So for K equals 1, you've got the actual ownership, you've got the predicted ownership, you can compute the error matrix. For K equals 3, you can do the same thing. K equals 5, you can do the same thing, and so on. Okay, so now, of course, the predictions were generated based on the majority rule, right? So it used the default cutoff, which is 0.5 in this 2-class situation. And based on that, the predictions were generated, as I showed you on the previous slide. So based on that, we can now generate the error matrix for each of them. And then based on the performance on these matrices, we'll choose the value for K, right? So for example, in this case, we can see an improvement from here to here, right? There is an improvement in both classes, right? So you're getting 10 owners, 5 non-owners, whereas here you're getting 12 owners, 3 owners. So performance on owners is better, and performance on non-owners is also better. There were 30 here, 31 here, right? So this is an absolute improvement between the 2 classes. Okay, whereas going from here to here, there is a deterioration in performance. Okay, these are numbers I just made up. Typically, you will see this trend that up to a point with increasing K, you'll see the performance is increasing. Beyond a point, the performance starts dropping off, and we will use this to choose our the best value of K, right? So we might do that based just on here we are using the default cutoff, and we may just go by the overall error rate. Okay, in this case, so we go by the overall error rate. The overall error rate is best for K equals 3. So therefore we say, okay, our best value of K is 3. Okay, then so that's what you're seeing here, the performance for the 3 levels. This is the overall performance. Okay, so here is 40 correct out of 50. Here you're getting 43 correct out of 50, and here you're getting 36 out of 50. So the best performance is for K equals 3. Of course, when we use the default cutoff, we are assuming that all errors are created equal. In other words, classifying as an owner as a non-owner is as bad as classifying a non-owner as an owner, right? But based on our prior discussions, we already know that this may not be the case. Okay, it could be the case that one kind of mistake is much more costly than another kind of mistake. So for example, if we stand to gain a lot by classifying an owner as an owner, and if we don't lose much by classifying a non-owner as an owner, right, then the errors are not created equal. So therefore, we would use a different mechanism to do the classification. We just won't use the cutoff probability. Instead, we may go by performance on a single class, or of course, we may use the ROC approach, right? Rather than making the system actually give us predictions, we will ask the system to only give us probabilities, and then we can generate the ROC chart and determine the cutoff. Okay, so for the current discussion, let's just assume that we are going by the default majority class approach. Later on, when we are looking at our code, we'll take a look at how exactly to do this with ROC as well. Okay, so now that we have built a training model and we have selected a particular value of k. Now we have to apply the model on the test partition, right? How do you do that? Well, what exactly is a model in this case? Interestingly, in the case of classification trees, our final model was a tree. And all we had to do was to take the test data and pass it through the tree and see whatever prediction the tree makes. In the case of KNN, the model consists of the chosen value of k along with the training A partition. That's the model, right? So if you want to make predictions for the test partition, then you have to run the test partition through the same procedure that we did for the training partition, for the training B partition. So we've got k, we know the optimal value of k that we have selected. So in the training A partition, we find the k nearest neighbors to each of these cases, get our predictions, and from that we make an evaluation of the test partition, of the model's performance on the independent data in the test partition. Okay, this is why I wanted to call the training A partition as the model partition, right? So the final KNN model consists of the value of k along with the training A partition. This is peculiar because KNN is the only method in which the model actually contains some data. In none of the other methods is any of the data part of the model, but in KNN it happens to be. Just to make this explicit, well, the content of the model in the case of classification tree is the actual tree. In the case of KNN for classification, it is the combination of the chosen value of k along with the data contained in the training A partition. So together they make up the model. So in order to classify a new case, we need both of these, right? So for example, you're given the test partition, take a row of the test partition, find its k nearest neighbors in the training A partition, and then classify it accordingly, or calculate probabilities, whatever you want. Let's look at the overall process. So first we normalize the data if required. Any numerical attributes have to be normalized or scaled. And if you've got non-numeric or categorical predictors, then you have to create dummy attributes for them. The next step, once you have done all this, is to partition the data, which is 3 partitions: training A, training B, and test. And then try several k values on training B, right? That is, for every row of training B, choose a value of k. First, you choose a value of k, and then for every row of training B, generate the predictions based on its nearest neighbors, k nearest neighbors in training A. Okay, so do that, and then generate the error matrix for every value of k, and then select the best k value, then apply that best k value on the test partition. If you like it, then deploy the model. And the model, as we've already said, is the value of k plus the training A partition that was used to build the model. Right, so that's what this is. So again, we got 86% correctness in the model. I just made up the numbers. Is it good or bad? Of course, as always, you have to look at something as good or bad only depending upon, without the model, what we could do. So I'm saying, let's say that without the model we could perform at 70%. Then with the model we are able to do 80%, 86%. So that's an improvement, probably. If this 16% in terms of the business, if that makes sense, then it would probably be a good model. Sometimes people also calculate what they call as lift. Okay, that is performance with model divided by performance without the model. Okay, in this case you're talking about just the performance on the overall error rate. Okay, not error rate on a particular class, but overall error rate. But you can see this is sort of quantifying the benefit that the model is giving you.